This is the effect of brine solutions on microplastic detection via density separation.
And I'm Maya Houghton.
I'm Kinsley Travis.
And I'm Gabrielle Smith. Microplastics are generally considered to be less than 5 millimeters in diameter, and they often pollute our aquatic environment. These plastics can end up in our homes and even in our food sources. Polyethylene and polypropylene are very common microplastic types. Little is known about what happens when these microplastics enter our body, which, as you can imagine, can be an issue. Within our experiment, we created 3 different brine solutions: sodium chloride, sodium bromide, sodium iodide. These were used to separate out our samples. Our research question is, what salt solution separates the different types of microplastics best?
So as you can see, we have our methods section split into 2 parts, and this is because our research is still a work in progress. We had only completed a few steps of our research before the global pandemic happened, but we are going to present our methodology that we plan to do in the future or to give to students in this class to do in the future. So our first step that we did included making our positive controls to test the brine solutions. We made the polyethylene sample by cutting and blending a milk jug until the pieces were around or less than 5 millimeters in diameter. These were then weighed and then suspended in water that contained some sediment. This same process was then completed using bottle caps for the polypropylene control sample.
The next step that we took was to make our brine solutions, and we did this by taking sodium chloride, sodium bromide, and sodium iodide and mixing them with water until they're about 6 molar in concentration. We then were planning on testing our brine solutions by putting them in a density apparatus with our plastic controls to determine which brine solution worked best with what plastics to push the microplastics up into the supernatant.
We are going to determine the best salt for density separation by comparing the initial mass of the plastics compared to the mass of the dried supernatant. The best salt would then be used to treat a water sample from the Cahaba River. So the next step in the future methodology would be to take a Cahaba water sample and filter it using a Buchner funnel, and then using Fenton's reagent to dissolve any organic material. Next, the brine solution that was best at separating the plastics in step 1 would be used with the Cahaba sample, and then the microplastics would again remain in the supernatant, and this would be tested and analyzed using FTIR analysis.
Although we do not have conclusions that are based on results, we thought we would share our expected conclusions based on research papers we have read in our own previous experience. The first is that we think that the NaI solution would have yield the best results because it has the highest molar mass and would be used in the future methodology. Additionally, because they are very commonly used microplastics, we expect to see fairly equal amounts of polypropylene and polyethylene in the Cahaba water samples, but we will not know this until the research is completed.
Let's say, with the implications of this research, currently there's not much known about the microplastic composition of the Cahaba River. And as previously stated, we know that these microplastics cause harm to the aquatic environment they're in, and then also cause harm to us as we are further up the food chain. This highlights just the importance of knowing how much microplastic there is in the Cahaba, as it's the main water source for the Birmingham area. Determining what brine solution that yields the best results will help us accurately measure the microplastic composition of the Cahaba with a smaller margin of error. Ultimately, more research needs to be done as we barely even got to start our project, but hopefully we'll be able to pick up later and then determine how these microplastics could be impacting our everyday life.